3I Atlas is gone. It passed Jupiter on March 16, 2026. It is now beyond Jupiter's orbit, heading towards Saturn. By July, it will pass Saturn. By April 2027, Uranus. By 2028, Neptune, then interstellar space forever. We will never measure it again. But before we move on, and the world has already moved on, because Artemis II launched and the Roman Space Telescope was revealed and the news cycle doesn't wait, I want to do something that almost nobody has done yet. I want to account for what 3I Atlas actually changed. Not what it suggested, not what it hinted at, what it permanently, irreversibly changed in the science of comets, in our understanding of the galaxy, and in how we will do astronomy for the rest of this century. Because the answer is more than any single object in the history of comet science. More than Halley, more than Hale-Bopp, more than 2I Borisov, more than any solar system comet ever studied. Today we go through every permanent result, one by one, what changed, why it changed, and what it means for everything that comes after. Stay with me. The scale of what just happened. Before we go through the results, let me put the observation campaign in perspective, because the scale of what was mobilized for 3I Atlas is itself historically significant. More than a dozen NASA science missions turned their instruments toward 3I Atlas. Few, if any, comets in history have been observed by as many spacecraft simultaneously. The list: Hubble Space Telescope, James Webb Space Telescope, SphereX, Swift, TESS, which actually captured 3I Atlas in May 2025 before the official discovery in archival data. MAVEN, currently orbiting Mars, which observed the comet's hydrogen coma using its ultraviolet spectrograph as 3I Atlas approached. Parker Solar Probe, Psyche, the asteroid mission, which captured 4 observations over 8 hours from 240 million miles away. Lucy, the Jupiter Trojan mission, which spotted 3I Atlas while en route to its targets. Punch, a solar wind imaging mission that captured the comet's tail. Stereo. And JUICE, the European Space Agency spacecraft, which contributed 5 instruments and 120 plus images. On the ground, ALMA in Chile, the Very Large Telescope, Hubble on orbit, Meerkat in South Africa, the Subaru Telescope in Hawaii, the Gemini Observatory, the Keck Observatory, and dozens of smaller professional and amateur telescopes contributing astrometry. The coordination required to point all of these instruments at a single moving target, calibrate the data across different wavelength ranges, share it between teams, and publish results in real time. That coordination was itself a new model for how science responds to a transient astronomical event. Thomas Statler, lead scientist for solar system small bodies at NASA headquarters who coordinated the observation campaign, said, 35 years from now, when astronomers have seen another 35 years worth of data on interstellar comets, they're going to be asking different questions. The way we leave a legacy so scientists of the future can answer the questions of the future is by having these data here and preserved for them to use. 3I Atlas team. That quote is the key to understanding what 3I Atlas means scientifically. The results we have now are the first layer. The results that will come from this data over the next decades are the part we cannot yet see. Permanent result 1. The DH ratio redefines water chemistry across the galaxy. The most significant scientific result from 3I Atlas was published yesterday, April 23, 2026. Using ALMA, astronomers measured the ratio of deuterated water, HDO, to ordinary water in 3I Atlas. The result, more than 30 times the ratio found in comets from our solar system, and more than 40 times the ratio found in Earth's oceans. It is the first measurement of this kind ever made for an interstellar object. Let me explain what this means. Deuterium is heavy hydrogen, a hydrogen atom with an extra neutron. Water can form with one deuterium instead of one of its 2 hydrogen atoms. That is HDO, semi-heavy water. The ratio of HDO to H2O in ice is set at the moment of formation and is exquisitely sensitive to temperature. The colder the environment, the more deuterium gets incorporated into the water ice. The lead researcher explained it this way. The chemical processes that lead to the enhancement of deuterated water are really sensitive to temperature and usually require environments colder than about 30 Kelvin, about minus 406 degrees Fahrenheit. The cloud of gas that formed the star and planets in the system where 3I Atlas originated was likely very cold, with very different conditions than the environment that created our solar system. 30 times above solar system comets, 40 times above Earth's oceans. This number is not a slight enrichment, it is a completely different category of object, chemically, from anything we have ever studied in our solar system. The permanent result, water chemistry is not universal. The DH ratio in water ice, which we had previously measured only in solar system objects, varies dramatically between stellar systems. 3I Atlas is the first direct measurement of water chemistry from another planetary system. It will be the reference point for every subsequent measurement of this kind. When the Roman Space Telescope and future observatories detect the next interstellar objects, the DH ratio measurement will be among the first things astronomers prioritize, because now we know it tells you something fundamental about the formation environment, temperatures, conditions, epoch, that no other single measurement provides. Permanent result 2. Interstellar comets carry prebiotic chemistry at record concentrations. The second permanent result came from ALMA's molecular detections in August and September 2025, formally published earlier this year. The methanol to HCN production rate ratio in 3I Atlas, 70 to 120. In solar system comets, that ratio ranges from roughly 1 to 20, with a median around 5. 3I Atlas is at 70 to 120. That is not an outlier. That is a different category. Methanol is a prebiotic molecule. It is a precursor to formaldehyde, which is a precursor to ribose, which is the sugar backbone of RNA. HCN, hydrogen cyanide, is the starting material for adenine synthesis, one of the 4 nucleobases of DNA, first demonstrated by Juan Oro in 1961. Both molecules are essential stepping stones in the chemical pathway from simple interstellar chemistry to the building blocks of life. 3I Atlas carried these molecules at concentrations 4 times higher than any solar system comet, in a nucleus 2.6 kilometers across, traveling at 58 kilometers per second through the inner solar system. The permanent result: interstellar comets are not chemically identical to solar system comets. The assumption that drove the design of most cometary science, that comets are broadly similar regardless of their origin, is wrong. 3I Atlas demonstrates that the chemical diversity of cometary nuclei reflects the diversity of their formation environments. A comet from a cold, metal-poor ancient stellar system carries a fundamentally different molecular inventory than a comet from our solar system. That diversity has direct implications for panspermia. The hypothesis that the chemical precursors of life are distributed across the galaxy by interstellar objects. 3I Atlas is the first direct observational evidence that interstellar comets can carry prebiotic chemistry at concentrations that exceed anything produced locally. The weak panspermia hypothesis that chemical precursors of life are distributed galaxy-wide is no longer just theoretical, it has a data point. Permanent result 3. The isotopic fingerprint of the early Milky Way. The DH measurement is the most recent result, but the broader isotopic story was established by 2 independent papers in early March 2026. The carbon isotope ratios, 12C, 13C, in the CO2 and CO of 3I Atlas, 141 to 191 for CO2, 123 to 172 for CO. Solar system comets, 90 to 120. The higher values in 3I Atlas mean less 13C relative to 12C, which means less stellar processing, which means earlier formation in the galaxy's history, before successive generations of stars had enriched the interstellar medium with 13C. A second paper from the VLT team measured the nitrogen isotope ratio from the CN molecule, 14N to 15N, and found it more than twice above the typical value for solar system comets. 3 independent isotopic systems, 3 independent teams, 3 independent instruments, all pointing to the same conclusion: 3I Atlas formed in the early Milky Way in a metal-poor environment at temperatures below 30 Kelvin 10 to 12 billion years ago. The permanent result: we can now read the isotopic fingerprint of the early galaxy from a physical object that traveled through it, not from stellar spectra, not from theoretical models, from a 2.6 kilometer ball of ice and rock that came to us, sublimated in our solar system, and let us measure its molecules directly. This is a new tool for galactic archaeology. Every interstellar comet we detect from now on will be subjected to the same isotopic analysis. Each one will add a data point to a map of chemical conditions across the Milky Way across cosmic time. 3I Atlas is the first point on that map. Permanent result, the number 4. The size distribution of interstellar objects is anomalous. The fourth permanent result is statistical rather than chemical, and it is the most unsettling one for our models. 3I Atlas has a nucleus diameter of 2.6 kilometers and a mass of approximately 1 billion metric tons. 2I Borisov had a nucleus of roughly 0.7 kilometers. 1I Oumuamua had an effective diameter under 200 meters. If the interstellar object population follows a standard size distribution, more small objects, fewer large ones, following a power law as observed for solar system small bodies, then for every object the size of 3I Atlas, there should be many objects the size of Oumuamua. The estimate: we should have detected at least 100,000 Oumuamua-sized objects before detecting a single object the mass of 3I Atlas. We detected one Oumuamua, Then we detected 3I Atlas. The implied size distribution is inconsistent with standard models of planetesimal ejection from planetary systems. Two possible explanations. Either we are dramatically underdetecting small interstellar objects, which implies the true number density of interstellar objects is enormous, straining the mass budget of protoplanetary disks, or the interstellar object population is genuinely top-heavy, more large objects relative to small ones than our models predict. Neither explanation is comfortable, both have been published, neither has been resolved. The permanent result? The size distribution of interstellar objects is an open problem in planetary science. 3I Atlas is the data point that made this problem visible. Resolving it will require more detections, which means waiting for the Vera Rubin Observatory to accumulate years of survey data and detect the population statistically. Permanent result. 5. The observation model for transient interstellar events. The fifth permanent result is not about 3I Atlas specifically. It is about how science responded to 3I Atlas, and what that response established as the new standard. All data from the 3I Atlas observation campaign was made publicly available in standard formats through NASA's Planetary Data System, the MAST Archive, and the IPAC Infrared Science Archive, accessible to any researcher anywhere in the world. Before 3I Atlas, there was no coordinated protocol for responding to an interstellar object. Oumuamua was discovered in 2017, and the scientific community scrambled to observe it before it left. Borisov in 2019 was handled better, but still without formal coordination. 3I Atlas triggered the first fully coordinated multi-mission, multi-agency, multi-wavelength observation campaign for an interstellar object. What that coordination produced is a template. Thomas Statler at NASA headquarters coordinated the agency's response. ESA coordinated JUICE. The ground-based community self-organized around shared astrometry protocols. The preprint server archive allowed results to be shared in real time before peer review, enabling other teams to build on each discovery within days. The permanent result, the next interstellar object will be handled better. The coordination protocols established for 3I Atlas, the data sharing standards, the multi-mission observation campaign structure, the real-time preprint communication are now the baseline. They will be refined, not reinvented. And critically, the advocacy for a rapid response spacecraft capability, a standing intercept mission that can be authorized and executed within weeks of an interstellar object discovery, is now supported by the concrete demonstration of what we missed by not having one. The Juno opportunity in September 2025 was real. The fact that nobody authorized the maneuver is documented. The scientific community will not let that argument be forgotten. What didn't change? The honest accounting. I want to be honest about what 3I Atlas did not resolve, because the permanent results exist alongside permanent open questions, and conflating the two does a disservice to the science. 3I Atlas did not prove panspermia. It demonstrated that interstellar comets can carry prebiotic chemistry at high concentrations. Whether that chemistry survives delivery to a planetary surface, whether it contributes meaningfully to the origin of life, whether any specific solar system object received a contribution from an interstellar source, all of that remains open. 3I Atlas did not explain its 22 anomalies, the 120-degree jets, the thermal insulation problem, the mass budget contradiction, the Nephi ratio, the sideways push that two independent teams measured differently. These anomalies are documented. They are published. None of them has a clean, fully quantified natural explanation. 3I Atlas did not identify its parent stellar system. The isotopes narrow the birth environment to old, metal-poor, cold, 10 to 12 billion years ago. But no specific star system, no specific galaxy location, no specific formation event can be identified. The trajectory cannot be traced back 10 billion years through a galaxy that has rotated many times since. And 3I Atlas did not answer the question that Loeb and others have asked explicitly and repeatedly: is the population of interstellar objects purely natural? The mass budget discrepancy, the anomalous size distribution, the geometric coincidences, none of them prove anything other than that our models are incomplete. But they are not resolved. They are open. The permanent results are permanent. The open questions are also permanent, at least until more data arrives. 3I Atlas changed 5 things permanently. It gave us the first direct measurement of water chemistry from another planetary system, 30 times more deuterated than any solar system comet, published yesterday in Nature Astronomy. It demonstrated that interstellar comets carry prebiotic chemistry at concentrations that exceed anything in our solar system, methanol at 4 times the solar system average. It provided the first isotopic fingerprint of the early Milky Way from a physical sample, 10 to 12 billion years old, confirmed by 3 independent isotopic systems. It revealed that the size distribution of interstellar objects is inconsistent with standard models, an open problem that will require years of Rubin observatory data to resolve. And it established the coordination template for how humanity responds to the next interstellar object, which is coming, probably within the next decade. Those 5 results are in the literature. They are peer-reviewed. They will be cited for decades. Thomas Statler said it best. 35 years from now, astronomers will be asking different questions. The data is preserved. The legacy is real. 3I Atlas is gone. The data stays. The questions stay. The 5 permanent results stay. And somewhere in the outer solar system right now, beyond Jupiter, heading toward Saturn, a 2.6-kilometer ball of ancient ice is continuing its journey, carrying the rest of its chemistry, the part we never measured, the pristine interior preserved for 10 billion years, back into the interstellar space it came from. Subscribe to follow what comes next, the next interstellar object, the Rubin detections, the Comet Interceptor mission. When the next one arrives, we will be here. And tell me in the comments, which of these 5 permanent results hits you hardest? For me, it's the DH ratio, 30 times above solar system comets, published the day after the flyby. The last data point, the strongest one.